So we're going to continue your probability and statistic part number 3. So last time we discussed about the normal distribution curve and the mean and standard deviation, how to use the area of the graph to come up with a product. Okay, here in this example, we're talking about the process and for your product, length right here, and we use the area to figure out, okay, the percentages of the product or the process. Are going to be between here and here, here and here. These are the ranges that we're studying. Of course, we use the mean and then the standard deviation and the area of the curve to tell us about these products. For this data set. And then in part 3, we're going to get into more about standard deviation. What does your data tell you? Okay, so standard deviation, when you think about the standard deviation, we're dealing with how spread out the data is. Okay, the data means the data set that you're studying in your graph. So we look at the data and look at how spread out that data is around the mean. Okay, when you think about the spread, you have a reference point that you're studying from, and that is your mean. Okay, we see the data are this distance far away from that mean. Okay, the data on this side are far away from this mean in this way. So even though we have normal distribution, we have many different shapes of normal distribution. And now you can see the two shapes. This guy is short and spread out, kind of like wider, and this guy is tall and you have see this is a narrow, the mean like tightly grouped around the mean. So all the data are in the first standard deviation, which is your first sigma. And when you look at the standard deviation, look at this, 0.1 is smaller than 0.2. So you can see 0.2, just by looking at the number, you get an idea that your data will be spread out, from both sides of your mean, which is this guy. And here, of course, if you compare to this, you know that your data is closer, towards your mean of 51.4. Okay, so that's how we visualize the standard deviation, understand the value of that, and link the value to the area, okay, of your normal distribution curve. So now we go back to our example problem. Is we're looking at the wedges and they have the length, and that's 51.4. Okay, for let's say this is a supplier 1 and supplier X is right here, and of course the wedge 51.4 is your mean, and average length, of course, of your wedges. And the standard deviation for the supplier 1, okay, wedges is 0.2 millimeter, meaning that it is more spread out, around the mean than the wedges from the supplier X, so whose standard deviation is 0.1 millimeters. So this is a narrowly grouped or tightly grouped, and then we can say like by calculating, so all of this are percentages. So if you calculate the percentages, then you know that 51.1, which is around here, 51.1 is around here, and then go all the way to 51.7 is going to be around here. It's going to give you approximately 99.7%. Okay, so all you have to I just show you right here in the previous example how I added up. And so that's what you do. You're adding the area, up together. It's going to give you 99.7%. I would say like 51.0 to 51.8 actually. Yes. So that would be a better one. So anyway, so 99.7% around, okay, because we are actually adding this little, okay, 0.1% around it. Okay, I changed a little bit. I think there's a little bit of a typo here, like whoever wrote this before me. And yes, so when you take a look at it here, for supplier X, if we go from 51.0, okay, all the way to 51.8 here, you're gonna get like 99.8. Okay, that's a 1 sigma, 2 sigma, 3 sigma, and relatively about 4 sigma in it. So that's a 99.8%. So this is how we calculate. So you will be adding up all of this. Okay. And then of course the next one is a supplier 1 going from 50.8 all the way to 52.0 is going to give you 99.6 because you're adding 3 sigma, yeah, 3 on this side, 3 on that side. So when you add from here all the way to here without including 0.1% like S and supplier X right here, yeah, you will get like 99.6%. Okay, so that's how we use standard deviation to calculate by using the mean, the area under the curve, and the sigma, which is your standard deviation, you know, intervals. Okay, so your data are inside of these intervals. Yeah. So anyway, I think you kind of get the idea of how to play around with that. Yeah. And then we come into a couple of examples here. You know, examples of mean and standard deviation. So you have a supplier 1, 2, 3, and 4. Yeah. And we can see our mean is 51.4. The spread is 0.2. Mean is 51.4. The spread is 0.133. Just by looking at the number, you know that this spread is wider than that one, which is tightly grouped right here around the mean. Yeah? The supplier 3 and 4, 51.2. The mean is 51.7. Yeah, so we can see the mean shifted. Yeah, from original 51.4 mean. So 51.4 shift to that side, 51.7 is shifted this side, 51.2. The spread is the same. Yeah, the spread is reduced right here. Yeah? See, the reduced mean like it goes even taller. Yeah. So make sure that you connect the numbers and the visualization. Yeah. So if you look at, if you see without the curve, yeah, without the graph right here given to you, just by looking at this, you understand that if you have an original, yeah, graph like that, then you know, like just by looking at 0.2 and 0.1, you know that will go taller. You know that the mean has shifted to this side or that side, which is on the left and on the right. Yeah. And you know that it's going to have the same spread because the standard deviation about the same. And here the standard deviation reduced half, yeah. So meaning like it's going to get taller than on the original graph like that, yeah. Anyway, so that's how we compare, you know, mean playing with the mean and standard deviations. Okay, then you have to understand, even though we measure the standard deviation, the area away from the mean, right? Your standard deviation does not depend on the mean. We only measure how far away, okay, your data point is from the mean, okay? And your standard deviation, meaning like your data point is deviated that distance from the mean. The standard deviation is not depending on the mean, okay? So make sure you understand that two points very clearly. So here we have three different distribution here given to you with a, what is that behind my bag? So we have a three different distribution with different means, but they all have the same standard deviation or spread of your measurements, yeah? So when you look at it, we have 51.4 millimeter, your mean, and your standard deviation is 0.133 millimeters, yeah. Another one, 51.2, the mean is shifted, yeah, meaning like it's going from 51.4 to that side, which is your left side. And then 51.1 go even further to the left side, yeah. And of course keeping the same standard deviation, so the spread is the same, meaning like the curve shape is the same, but the mean is shifted to that side. So this three example is telling you, even though the mean changes, standard deviation doesn't change, okay? Because standard deviation is only the spread or distance measurement from the mean. So the mean can change whatever, yeah? If the standard deviation is the same, the spread is the same, yeah? So that's what it's talking about here. Then standard deviation as a function of your distribution shape. So when you take a look at it, now we're getting into the mathematics, yeah? And this is another time the student go crazy again, yeah? Don't go crazy. Everything is fine, yeah? So standard deviation, we're going to use it as a function of a distribution shape. So here we have normal distribution. So here we are studying, okay, two distribution. And one is our normal distribution and the other one is our beta distribution, yeah? So when you take a look at, they have the same mean, which is 100 millimeter. So the mean is 100 millimeter, and the standard deviation for normal is 0.15 millimeter, and your standard deviation for the beta distribution is 0.2236 millimeter. Okay, so in normal distribution, most of the values are, when you look at it, they are tightly, clustered tightly around the mean. And the spread, of course, when you look at it, is more concentrated near the center, and this makes the standard deviation smaller, because fewer values are far away from the mean, meaning like the value here are fewer than the values inside of the first standard deviation. So that's what we're talking about. So in beta, when you look at the upper curve, you're going to see the distribution also has a mean 100 millimeter. I've already showed you that, and the shape is more spread out. So and the values have like a greater range around that mean, meaning like look at this, a standard deviation which is greater than our normal standard deviation. 0.2236 is larger than 0.15 millimeter. So the standard deviation which is higher than that of the normal distribution. So the higher standard deviation indicates that you have more values that are far away from the mean, far away from the mean, so causing the distribution wider, so you can see the wider curve in beta distribution. So when you look at the standard deviation values and when you compare to another standard deviation value, you can understand that your curve is wider or tightly grouped around the mean by looking at which value is higher. So if you have a higher or larger value, that means your curve is wider or spread. Your data points are spread out far away from the mean. So this is how you interpret the two distribution here given to you as an example. So normal distribution has a tighter grouping around the mean, meaning most of the data points are closer to the mean, which is 100 millimeter in this case, and it's going to result a lower standard deviation. The beta distribution have more parts that are far away from the mean. The mean is 100 millimeter, the same, leading to a higher standard deviation, which is 0.2236 millimeter. So even though both distribution have the same mean and cover the similar range, they are different if their standard deviations are different. So standard deviation is a measure again of how spread out your data points are. So if more data points are far away from the mean, the standard deviation increases. So the beta distribution has a larger standard deviation because the values are more spread out compared to the normal distribution. So even though both distributions span similar ranges, or value. So I say similar ranges of value is because of this lower and the upper is the same thing, and then of course the mean is the same. So this is teaching you here on this slide is telling you the two distribution, beta and your normal, with the same mean and a similar range can have a similar range from here to here. They can have different standard deviations. One is this and the other one is that. Depending on how the values are distributed, your data points are distributed around the mean. Of course, this is your mathematical definitions of your standard deviation. So our line is engineering technology, which is not like the pure mathematics. So therefore, you don't need to remember all of that, because we heavily use a program, computational program here for you is Excel in this school, But of course, depends on what you're doing. We use a powerful computational programs, And of course, different kinds of stuff. We use MATLAB, Python, etc., etc. And also, we also have other ready-made applications for computation purposes. So anyway, so here when you look at the standard deviation, you see that the mathematical equation or mathematical model looks like this. And you of course need to know what they are. This is just rewriting the same, getting the standard deviation, but we're rewriting that equation into this by spreading out this, sum. So see, then we're adding, meaning like going from 1 all the way to n. So we go from 1 all the way to n here, see? It's not that difficult, of course, yes. And of course, now we're gonna break that down. Yeah, this formula into a separate section, so you can be able to understand. So the very first thing is your individual measurements, which is your x right there. Yeah, these are your measurements of values. Yeah, and then of course you can calculate the sum, and then we can calculate the average, and then this is showing you how we can get the sum is right here. You know, going from 1 all the way to n of your x, which is your data point right there. Yeah, this, when you look at it, see x1, and then you go all the way to xn, and we sum it up. So use this little sigma sign, just a symbol for telling you that, hey, we're adding, yeah, adding 1 all the way to n, and we're adding xn, yeah. And then of course and that x come from this little x, okay. And the average is your x bar, and x bar is how we calculate that is your sum, okay, divided by n, yeah, which is the number of your data points. So if you have like 25 data points, it's going to be 25, yeah, and of course you're going to have a 1 all the way to 25n, yeah. So that's how you read. And then of course number 3, you're going to subtract the mean from each one of them, meaning like we are subtracting that from each of the data set. Yeah, so getting into here, and we do that. You know, after that we're going to square that result, just square it, because it said it. So we started from here. Yes, we get the sum. Yes, we also get the sum, yes, of your x, and you subtract all of that and then square it, okay. Then you're going to get the sum 2 divided by n plus 1, yes, and then take the square root, okay, out of it. So it's just like we're following each one of them here, yeah. And again, I put it here so you don't have to do the whole thing, yes. All you have to do is just use your Excel, which is this guy right there for you. And if you call the standard deviation, you're going to see this. You know, we have a sample standard deviation, and then we have a population, so make sure that you choose the correct one, okay. And we have, of course, several different standard deviation. Anyway, so this is your sample standard deviation, okay. So right now I'm just going to erase this because just want to show you where the formula is in Excel sheet. So I will show you again. Yeah, see, STDEV dot S is your sample. Yes. Okay, so I hope you see it, which is written here that for you. Okay, so this is a formula that's going to help you measure how much the data points deviate from the mean on average. So the standard deviation is commonly used measure for the data dispersions, yeah, in the statistic, and I've already showed you many different graphs. Yeah, in Excel we use the STDEV dot S function for a range of your data points, so we can easily calculate that. Yes. So of course, if you have time, make sure that you understand the foundation mathematics models, and you gotta know each one of them. I just explained that to you. Yes. The very first thing is you got to understand what we're doing. Yes, inside of that formula. So when you look at the mathematical definition of that standard deviation, you see this formula, and we can write it in 2 different ways. Yeah, and your sigma, which is this guy, is your standard deviation, and you have to know each one of the term, which is n is your number of data points. Your little x, I all the way to going 1 to n is your individual data points. We call it data points or measurements. And then your x bar, you know that, and that is your mean, your average of the data points, yeah, the one in the center that we usually draw in our normal distribution. And then you are going to list all of that out, which is x1 all the way to xn here, yeah. So write down all the data points that you have, yeah. And then you're gonna find the mean, okay. If you find the mean, all you have to just add them up, yeah, add them up, and then divide it by the n. And that is going to give you the mean, which is showing you here, yeah. So this is, oh, please add them up and then divide it by n. So if you use Excel, your mean is, or you have to just get the average, okay. So if you get the average, you're going to get return the average, okay, arithmetic mean for you, this guy right there, yeah. And that's what we're doing right here, yeah. We added up the sum, and then in the mathematical formula is this guy. And then we are going to get the mean, which is we're getting that, okay. So sum divided by the number, which is n, and that's what we're showing here. I'm explaining that again for you. And then we're going to subtract that mean from each other data point. So that's what we're doing here because it said it, so please do that. So we're going to divide it by n, and then we're going to subtract that mean that we just calculated from each of the data point. And then we're going to square the result because it said it so here too. Please square the result. So square the differences you found in step 3, okay? And then square them up to remove the negative values. Squaring is good because we don't want to deal with the negative values in the mathematical formula, So we usually square it and get rid of the negative values. And then we're going to sum the squared differences, you sum it up, meaning like add them up. Sum, you can easily do this by calling the sum function here on your Excel sheet, which is this guy, add all numbers in a range cell. So I'm just going to delete it here for now and then go back here. So anyway, so that's what we're doing here, summing that up. So after you have summed that up, what you're going to do is you're going to divide the sum by n minus 1, okay? Why? Because it said it so here 2, So therefore n minus 1, we divide with that, Take the square root and take the square root of that. The sum, okay, divided by n minus 1. So finally, taking the square root of the result, step 6, and you're going to get the standard deviation, So anyway, this all been done by giving this program Excel is very powerful. It's a computation spreadsheet. So you can use it, call the function, and give the data points. And all you have to scan and call the function stdev.s. That will give you everything that I just told you right now. So you know that xi is the individual measurement or data point. You know that n is the total number of measurements or data points. Your x bar is just simple. The mean average of all the measurements. And then xi minus x bar is the square difference, and to the power 2. So this whole thing is telling you the square difference, between each measurement and the mean. And then of course this little sum, sigma, so that's just your sum symbol, which means to add all the values together. So now you understand what you're doing. First, you list the individual measurements. Second, you calculate the mean. And third, you subtract the mean from each data point, and then you square them up, square each difference. And then you're going to sum, all the squared differences, and then you're going to divide it by n minus 1 to get the variance, And take the square root, it's going to give you the standard deviation. Okay, so that's what we're doing here. All right, then let's go to the next slide. Alright, so here is your Excel, how to calculate mean and standard deviation, and I am going to go over that for you. And here is our example sample data, and when you look at it, these are called the data points, and this we call it x1, 2, 3, 4 all the way to n is equal to 10 here in this example. And let's go ahead and see, like before we draw this, we can be able to first, of course, you're going to copy your data. The real world data is not simple like this, not 10, definitely. They are in thousands, and you have to do this every day in your life. So first we copy the data set like this, okay? What I'm going to do is, I think I should, part 3, okay, relatively around here, part 3. Excel is going to start, okay? So I write it here, so make sure that the part 3 is going to start from here. So anyways, so first we copy, okay, a data point. Here is your data point, and then of course you do it like x1 and etc all the way to xn, which is your x10 in this case, okay? So therefore you know that n is equal to, you have 10 data right now. Okay, so anyways, first what you have to do is finding the average. All you have to do is call the average function, which is this guy. You go AV and it's gonna come, and all you have to just scan this, okay, all the way to the end of your data set. Okay, and when you calculate it, you're gonna get this. Of course, we usually format decimal like that, yeah. So you get a 42.53. The standard deviation, okay, is you need more accuracy. So we usually format about a 4 decimal place. So standard deviation, we're doing the sample, so therefore we're gonna choose this, yeah, the guy. And after that, we're gonna scan it, the whole thing, yeah. And then of course close the bracket, and it's gonna give you in standard deviation, we're gonna give it 4, yeah, decimal place to make it a little bit more accurate. So anyways, and then for range, you have to first find the maximum, yeah. So therefore we find the maximum, and which is this guy right there, yeah, and scan it, the whole thing, yeah, and then close and enter, and it's gonna give you your maximum, yeah, data point out of your data set right there. So this is your data set, and each one of them is your data point. Don't come and tell me what is this one. You type it in, yeah, x2, 3, 4 all the way to 9, yeah, and then find like a minimum is gonna go like that, and then do all the way down, yeah, and then calculate, so you get your maximum, minimum, and then you can find the range. So your range is maximum minus, yeah, and then minimum, and it's gonna give you your range right there. So anyway, so that's how we calculate, okay. So I'm just going to erase it because I don't want to give you a redundant set right there. So your average, standard deviation, sample, don't forget that. Your range is based on your maximum and minimum data points of your data set, okay? So anyway, so that's how we calculate, so that now you know your mean is 42.53 and your standard deviation is 0.2930 here, yeah? So when you calculate the mean and the standard deviation using, you know, your Excel or your calculator, of course, here I don't want you to use a calculator, yeah. So I am going to go ahead and just get rid of this one for you. So I get rid of the calculator because if you use a calculator, you make a lot of mistakes. Yeah, so make sure that you use your Excel. You have your Excel given to you with your tuition fee. Yes, so you should envision the curve above, and then you should think like in terms of 68.2% of the items being between your plus and minus 1 standard deviation, yeah, of the mean, or between 42.2 and 42.8, right, in this case. So here 42.2, 42.8 is going to be having this area under the curve, and that is 68.2%, okay, out of your 100 items. So meaning the data 68.5% of this 10 points is going to be right in there, yeah. So if you calculate how many points out of 10, okay, you can do it in Excel like this, yeah. So 68.2, right? 68.2%. Oh, what am I doing? So you have 68 point. Oh, where is my stuff? So anyway, so 68.2, yes. And then time, of course, you have 10 points right now out of 100. So 6 points out of your 10 points is gonna fall in that area. Okay, so that's all what it's talking about. So you're gonna see 6, all right, data points in here. Yeah, if you want to know how many data points are going to be in 34.1, all you have to do is do the same thing, 34.1, all right, times 10 divided by 100, okay, is about 3 points is on that side, okay. So 3 points on this side, 3 points on that side. 13.6, how many points are going to be in there? So 13.6, and then of course time 10 divided by 100 is going to give you about 1 point is in there, yeah. So 1 point, so 3, 3, 6, 7, 8, of course 9, 10 is going to be right in there for you, yeah. The next one is 2.1, yeah, so about 1 point, so 2.1, and then times 10 out of 100, so less than 1 point. So anyway, so you're gonna get about six points, okay, and then about 1 point. Around this area, okay, so that's how the data points are spread in that area. So that's what basically what we do, okay. Okay, so from here to here, the standard deviation, the spread is 0.293. So meaning 42.5. So if you add 0.293 to 42.5, you're going to get relatively 42.8. Okay, so see, that's your first standard deviation. And then you add another of this to this, and you can be able to get, okay, these millimeters in this example. Yeah, and do the same thing on that direction. Okay, so you now know what to do. I can show you, yes, if you want to go to the negative direction, 42.5 and 42.2. So all you have to do is minus that, 42.5 minus 42.2. Yeah, it's going to give you about, see, 0.3. So that's if you want to look at the accuracy, we're going with, I think, 4 decimal point. So you can be able to get, which is this guy, yeah, so 0.2930. So if you do 0.293, yeah, and you want it in like let's just say 1 decimal place, like that. I'm just showing you, yeah. So if you just go like 1 decimal place, see, about 0.3, yeah. So that's you're adding 0.3 to the middle, which is your mean. So that's the first spread, which is 0.293. See this little yellow arrow right there? Yeah, so and that's how you add for each of the standard deviation, okay, or the sigma. So we call it 6 sigma, so 3 on this side, 3 on that side, so altogether 6 sigma, so all of your product data points that you can be able to see. Yeah, so quality people like us, we do this very heavily every day. Okay. Okay, then we go into the probability distribution, and you have already studied probability, which I'm gonna roll this and then show this thing again for your dice problem here. Yeah, so you know that the shape, okay, of your histogram of a process would look like, okay. So the probability distribution definitely is connected to the shape of your histogram. Yeah, and we use them to estimate the probability that a variable will fall within a range, okay, of length, or that just is an example of your variable is a length or temperature or thickness or whatever you are studying, okay. So that's what we're looking at. So if you don't want to get into confusion, all you have to know that we use the histogram, we use the probability distribution, okay, and especially the histogram, the curve, right, and the values, and to estimate the probability that your variable is going to be. Yeah, so standard deviation, here you understand how to look at the standard deviation. You know the mean, okay, which is your x bar right there. You know how each standard deviation, okay, is spread out from the mean, yeah, increment. You go 1 standard, 2 standard deviation, 3 standard deviation, okay. All you have to just add it to your the variable that you are studying, okay. And then the normal distribution, here in this example we have a shaft, okay, and we are looking at the diameter, and we're doing about 1,000 shaft, yeah, measuring the diameters. Our interest is the measurement of your diameter, and then we're measuring 1,000, right, shafts. And when you calculate the average of your measurement, you get 27.10 millimeter for your diameter, okay, of that shaft. Standard deviation we calculate in this way that I just show it to you. Yeah, so you measure, and you're gonna get 1,000 shaft diameter, and then you're gonna calculate your average sample, right, and your range sample standard deviation, and this is where the data come from. So you get 27.10 and then 0.05, and then we're gonna put them all together and draw the normal curve. You can do it by using the Excel to draw the curve, and we can be able to see the sample mean and then the standard deviation line. You know that the standard deviation, each one of them is 0.05, added to your mean, okay, which is this guy. So don't come and tell me like, oh, I don't know how to write the number here. You know it. As soon as you get the mean, you can be able to write mean, and the standard deviation will give you all the numbers that you ever wanted. Yeah, so all you have to just add this okay, to this, and you'll get that, and add another standard deviation to this, you'll get this, and add another standard deviation to this number, and you will get that. Okay, do the same thing on that side. Yes. So when we look at the 99.7% estimate of shaft diameter is going to be between 26.95 all the way to 27.25 millimeters. All right. Okay. The next thing I am going to tell you about is the area. Yeah. So the area under the curve is what we have just calculated. We calculate the mean, we calculate the standard deviation based on the data set, and then we draw each standard deviation on this side, on that side. And now we're getting into the area under that curve. And I've already taught you right here, the area under the curve is completely your probability, okay? So this is what we're doing. Yeah, so the area under the curve is going to give you the probability of, okay, here in this example is your length, your diameter actually, so diameter value is what we're doing here. You can be able to get that diameter value, the probability of that diameter value by looking at the area under that curve, okay, in that value. So if you want to know the probability of 27.15, okay, out of all the 1,000 shaft diameter that you just measured, all you have to just get that area and it's going to give it to you. Yeah. So how easy the probability is to calculate. Yeah. So don't come and tell me I don't know how to do it. You know how to do it. It's super easy, super easy. Yeah. Because the entire area, that's starting from this tail all the way to that tail, so the whole area, meaning like the area of all of the sum of this a little grid, is going to give you 100. So now I have like a 1 2 3 4 5 partial grid right to here. So you can be able to get the area of that, and that is the probability of this length right there, this diameter right there. So that's basically what's talking about here. Now here we have a yellow, so shaded, that's a total area under the entire curve is always 1 or 100. We call it 100 is nothing but it is writing 100, okay, in a decimal. So if you have like, let's say, if you have 100, okay, 100%, we usually write it at 1.0 in decimal. If you have like a 90, all right, percent, okay, if you want to change that into decimal, what you have to do is you're going to divide it, okay, by 100, and it's going to give you 0.9. Yeah, so this is a decimal, and this is written in the percent, okay. So if you have like a 80, the same thing, okay? You can equal to, and then 80 divided by 100, and it's going to give you. If you have like a 0.7, and you want to change it to percent, all you have to do is 0.7 times 100, okay? So some students still are struggling, and I don't know why, okay? It's just so easy. You're going to do like a 0.6 and then time 100. Okay, and you should be able to get back and forth like that. So if you have 50%, all you have to do is 50 divided by 100, and it's going to give you 0.5. Okay, so if you have like 0.4, and if you want to change back to percent, all you do is 0.4 times 100, and it's going to give you, what did I write? Okay, so 100. So 100, and it's going to give you 40, okay? So we do the same thing. You have to do, okay, back and forth like that. So when I was a student, this is what I do. I play this way, okay, back and forth, and that just give me, so you have 0.2, 0.2 times 100. So if you do like 1,000 times, okay, you'll definitely get how to change it back and forth. So all right. So that's a pretty easy, okay? So 0.1 all the way to 1. So 1 is 100, 0.9 is 90, 80 is 0.8, 70 is 0.7. So if you do have like something like 35.6, okay, percent, you do the same thing, 35.6, and then divide it by 100, you're gonna get 0.356. So, and then if you have like a 0.654, something like that, the same thing. Okay, 0.654 times 100, and it's gonna give you the percentage. Okay, now you get a whole of it. So when you look at it, see 35.6 is a decimal, your 3 is on the first decimal, your 5 is a second decimal, your 6 is on the third decimal. So all you have to just move that a little decimal. So if you see that 0.356, I know I have to go backwards 2 times, yeah? So therefore 35.6. If you have like 0.65, I know that's 65.4 without even calculating it. Okay, so if you have like a 006 like this, okay, now I'm gonna go like 0.65 like this. So what is it going to be? Now I don't even have to calculate it. I know for the fact that is 6.5%. Okay, so if you don't believe it, you can also calculate it. See, 0.065 times 100 is definitely give you the same answer. Yeah, so if you do have like a 0.00 and then a 4 right there, so what is the percentage of that? All you have to just move a 2 decimal to the back, and you get like 0.4%. If you don't believe it, you can do the same thing again. 0.004 times 100, it's going to give you 0.4%. Okay, so make sure you play with this and try to get back and forth between the percent and the decimal, for your reading the area of that. Okay, so make sure that you do that. So the probability that the variable takes on a value somewhere on the curve is 100. So the total area under the curve is 100%. Yeah. Okay, now we're gonna start with a little problem right here. So you are given probability distribution, and that distribution is again length, so this is we're measuring that shape of diameter, so still the length of widgets, and we pick a widget at a random. We just like take one widget out of that 1000 diameter measurement you just did. So the question is it more likely to fall in this range, in that range, or in that range? Okay, and you have to answer why. Okay, so let's see. Of course, if you get straight into this, you wouldn't understand because you forget about the sigma and everything. So you have to go back here to the very beginning, that the sigma is here. So you have a 27. This is where in the same problem. So you have a 27.1, and then you have a 0.05. Okay, for your sigma value. Yes, and do not forget that. So the problem right here is based on that, okay, sigma value. And then we are going to go, okay, to the left side, which is a negative. So you will go like 2.3 sigma, okay, go to that side. So 1 sigma and then 2 sigma, yeah. And then you can also, so the range is like minus 2.3 and then minus 1.25, so which is this guy and that guy, yeah. And that is going to be your area A, yes, and that is given to you. So this is given to you in your problem, yeah. So that is 6.5%. So 6.5% out of 100, yeah. So that's how you calculate the probability. So if you go straight into it, you can't be able to get it, okay, right away out of here, yeah. And you cannot get, all right, some students didn't know, and then they will stay on this slide for a long time trying to get there's a 9.5 out of the given. It's not enough, right? So because that's not the way that we do a calculation. So in order to find, all right, in order to find the probability that the variable will take on a value in the interval of this little a, okay, and we're talking about is actually 9.5. So this answer actually comes from cumulative distribution function, okay. So we definitely need to get the cumulative distribution function values for this range, okay. And we use something called a Z table, or sometimes we use a computation, right, devices, also software, easily called. and calculate the probability for that normal distribution. Okay, your norm or disk. Norm disk is called the normal distribution in Excel. Yeah, so don't attempt to calculate anything right now, and we will continue the lecture, and we'll be showing you how to get the accumulated distribution function. Yeah, and then we're gonna get back to that. Okay. So how do you get this? This is just we're picking a diameter. So pick a shape because you're measuring the diameter of a shape, and you have 1,000 shape at the in this problem to measure. So a shape random out of the 1,000 shapes, and you get 9.5% of the time it's going to fall somewhere in that area, which is your range A here. Yeah. So again, the main point is, of course, from area B is a 3.7 and area C you have a 3.9. Why? Because your sigma cutoff, sigma ranges from here to here, from here to here. Yeah. So anyway, so in order for us to be able to come up with this probability, the very first thing that we have to do is to look up the cumulative distribution function before we ever go into it. And in order for us to do that, we need the Z table. Yeah, and we will continue with the lecture. So and show you an example how to do it and come back to this problem. Yeah. Okay, so now I am going to show you. Okay, and this is your Z table. Yeah. I'm going to make it a little bit smaller so you can see this is called the cumulative normal probability tables, and we call it Z table for short. Z values are written here, so for you, so I'm just going to make it a little bit bigger, and this is your positive, values, and the second page is going to show you the negative Z values, so when you go back here, you have a minus, the starting point, we usually start with the lowest value, which is your minus 1.25, which is this guy. Yeah, so minus 1.25 is sigma. Yeah, so if you go to the Z table, you're going to go to the minus, which is this guy. Yeah, and 1.25, so 1.2 is here, and then you go all the way to 5. Yeah, so if I'm going to make it a little bigger so you can see it a little bit better. Yeah, so when you look at it, 1 minus 1.2, and you go, because this is going 0, 1, 2, 3, 4, 5, so that's 1, 2, 3, 4, 5. Column number 6, is 0.5. So we go minus 1.25. So you go 1, 2, 3, 4, 5. Here. So we get 0.10745. Okay, 0.10. So actually 0.1074. And the next one is a minus 2.3, so which is this guy, 0.00842. So we write this as 0.00842. Okay, so this is your area A. Yeah, how to calculate it, and then what you have to do is you subtract that. Yeah, you get about 0.09907. Okay, so that is actually 9.9%. Okay, which is a little bit contrary from this. Okay, this is written on 9.5. So it also depends on which table. Okay, now this is I got it out of the internet. Okay, I downloaded it. And so also it depends on which table that you're using. Because Z table, they have a little bit of the variation. Depends on who is producing that table. Okay, so slight differences is not much, but you can also use the norm disk in your Excel function. And this is just showing you with this table that we're calculating. So yes, this value that like in the slide getting is maybe like from the different tables that he was using. Also, of course, when we pick a shell, right, and that is going to also give you a different value if we use the Excel. So there's a slight variation of the probability, but you will get around around 9 point something percent. So slight variation is that is okay. I'm just showing you easy, okay, way for you to be able to get it by using a z table, yeah, manually, and calculate right here instead of using the norm. Because if you use a norm this, you can also do a norm distribution, okay, for sample is going to be this one, yeah. So if you go like this, you need the z number and then the cumulative, okay. So if you go like the z number, we can put which I'm going to show you right now why there's a little bit of difference, yeah, is that so if you use the norm this, and norm this for sample is this, yeah, that's for population. So we are going to use a sample, and your z number is a minus 1.25, yeah, and then of course we are going to give it true because we're looking for the cumulative distribution function is true, yeah, and then you press enter. Sorry, I have this sorry about that. I have a typo here. It's gotta be TIUE, and it's gonna give you, okay. So see, there is this one is from the paper, yeah. This one is we use Excel, so we have a slide, yeah, variations of the value here, and I'm gonna just do that a second time again here, yeah. And I'm gonna give it TIUE true, and see like how different the numbers are, yeah. The one from the z table, paper z table value, yeah, is we get this is doing nothing but we are subtracting it, yeah. So all you do is I subtract this out of here, and that is gonna give you, just go minus and then this, okay, and that is gonna give you 9.5 that you're looking for, okay. So now I'm just gonna just give 2, yeah? 2 is a better accuracy than that, and I would just go 4. It's better accuracy, okay. So anyway, so then we're gonna change that, okay, into percentage, so that way you can be able to see the number of it, yeah. And then I'm gonna give this as a 1 decimal, so that way you don't feel bad to look at the slide answer, yeah. So anyway, so this is what I'm talking about, yeah. So if we use Excel, you're gonna have a little bit of a different, okay, answer than using this paper z table, yeah. So calculating the same, this is your sigma, which is your standard deviation, okay. And then we calculate for Excel, we use a norm disk, okay, for sample, by the way, sample norm disk. So don't forget the sample disk mean distribution, okay. And I'm going to show you very slowly here again. When you go norm, that is not correct because that isn't the sample. This little s in there, see, so norm dot s dot dist is the one you would be using, okay? So if you collect like this way, and I can just write the name for you, yeah, so that way you will remember what I'm doing here, okay. So anyway, let me just print a little highlighted here for you, okay. And of course we want to keep this one about 4 or 5 significant right there. So let me just go about 5 here is fine. So now you can see everything, okay. So I can make it the same as your z table 4 is fine too, yeah. So now z table can go 5 sometimes. So if you look at it 1, 2, 3, 4, 5, yeah, they go 5. So we can make it 5. So that way you can be able to compare the z table and the norm sample disk that we're doing, yeah, norm sample disk distribution. So sample distribution is a little bit different from the normal distribution, normal population distribution. So anyway, so now you understand the difference between this 9.5, yeah. So that's because we heavily use the Excel, you know. So for pure mathematics, they're gonna use a paper thingy, yeah, the one that I just showed this to you. of course, we can be able to calculate this one. So the next one is area B. So you have like a 0.3 and then 0.4. Yeah. So we do the same thing here for area B. Okay, I'm just gonna put it here B, and we are gonna find our CDF. Yeah, united distribution function, and our sigma is given to you as standard deviation. Okay, is given to you here as 0.3 and 0.4. Yeah? So we have 0.3 and then 0.4, and first you have to find the z value. Yeah, and we're gonna use a norm disk because it's faster for you. So I'm just gonna go ahead and do that. Give the standard deviation, and then we want the CDF. Yeah, cumulative distribution function. So just enter that, okay? And we do the same thing, okay? And I'm gonna show you again. So I think you should be able to get this by now, yeah? And then a comma, and then give it a true here. So you will get that, okay? All right, and then all you do is minus, yeah? Minus it like this, okay? And then you change that into percent, okay? Of course, you can give two significant figures of one or decimal place, so you get a 3.8, okay? Of course, that depends on what we're trying to do here, because we gotta go actually 5. Yeah, so that's the accuracy. So we play with a little bit of the and that is going to give you that, okay? So anyways, for my Excel, right, with the 5 decimal places, and I get like about 3 point, okay, 3.8. Of course, here he is talking about 3.7, but that's okay because I have no idea whether he's using the paper or the Excel. Okay, even Excel sometimes a little bit different and how they are inputting, but I can change this to 3.8, and I also fixed this for the slide has some typo here. Yeah, so this got to be a 9.5, and this one is going to be 3.8. So let's check if this is okay or not. So 1.25 and 1.5 for C, 1.25 and then 1.5 for C. Okay, so let's do DV here. And we're gonna do the same thing, okay, on this. And then true. And then we will calculate that. Alright, so we get this. So we wanted about 5. So just go and 5 here, yeah, and subtract that, and change that into percentage, okay, and it should give you that. Of course, so we change this into 1 decimal, go down, so that's about 3.9, okay. Well, anyway, so this is what I got, yeah, from the from our Excel, which is maybe a different different Excel we're using, yeah, because the former professor, yeah, former professor is maybe use a different version of the Excel, so a little bit different, but it shouldn't be, but it's okay, yeah. So anyway, so there's a slide, or maybe it's just a typo, I don't know. But anyway, so this got to be a 3.9, so yeah, he get this correctly here, yeah. So anyway, so so these are what we need to do. I will definitely update those files for you, so that way you can get the correct version of it, okay. So now you know how we get Anyway, so now you know how we get, okay, all these probability. Probability is the area under the curve, and we calculate this way. You're gonna use the standard deviation, which is this line and that line, okay, this line and that line and this line and that line. So after using the standard deviation, we have to find the cumulative distribution function. We call it CDF, and you can use very easily, okay, your XL, which is your norm sample distribution, okay. So if you use that, you can be able to easily calculate that, okay. So that's how we get the probability under the curve, yeah, which is your area. So if you pick a shell, yeah, so the shell has a diameter that we're measuring, and randomly out of your 1,000 shell, and that will likely fall into about 9.5% in range A, about 3.8% in range B, and then 3.9% in range C. Okay, so that's how you answer that question. So and then we will of course getting in details, yeah. So what I'm going to do is I'm going to take a break right now, and then I will record the part number 4, yeah. So getting into the calculating the area in an interval, step by step for you. Yeah, I have already taught you how to do it in Excel very easily using the function. Yeah, so computational software are very useful because they cut your time for you. Yes. Anyway, so we will get into the pure mathematics and how to do that step by step for you, so you at least get the foundation.